Hello everyone. How are you doing? Can you hear me okay? Sound okay? Excellent. Everyone's doing well. Probably give it a couple minutes and then go ahead and get started. Just wanna, as always, let people roll in if they're getting notifications, so on, so forth. Okay, it's looking like people are starting to roll in, so I think might as well go ahead and get started. Um, so yeah, the last time we did this, we spent quite a bit of time sort of sitting down and deriving a new formalism for classical mechanics, namely Hamiltonian mechanics. And sort of the big deal about Hamiltonian mechanics is that it doesn't really depend on what choice of coordinates we use. And we saw last time that this has some advantages, and we get some things for free that we maybe didn't get without some sort of mathematical and mental gymnastics in standard Newtonian mechanics. So this time, I want to actually use it some more. So go through some examples and hopefully convince you that this is a much, depending on who you ask, a much better way of doing classical mechanics than Newtonian mechanics, which can be at times quite confusing and quite difficult to deal with. So today's gonna be pretty simple. The things that want to do is just sort of work through some problems using Hamiltonian mechanics. And so, as the title of the stream might suggest, one of the big things that we're going to be talking about is gravity in this. I felt like we haven't really had a big chance to talk about gravity more in depth yet, so wanted to really get some more insight from that. And so, yeah, sort of keeping in mind this whole time, trying to see how Hamiltonian mechanics can help simplify problems which might be very complicated in standard Newtonian mechanics. And also, we'll see that this Hamiltonian formalism can just sort of give us some extra insights into physical systems in general without having to, again, go through all the work that would be required to see that in the Newtonian case. So, of course, as always, feel free to drop any questions you may have. Seeing lots of people in the chat already saying hi to everyone in the chat. So, yeah, without further ado, go ahead and get started. So, just as a reminder, when we're dealing with Hamiltonian mechanics, The main ingredient is, of course, I should probably actually be writing, the Hamiltonian. Which we write as a function of what we might call generalized momenta and generalized coordinates, P and Q. So these are, I'll just call them general momenta. And these are generalized coordinates. Where, again, remember, this is all true no matter what we choose for these momenta and coordinates, as long as we do everything consistently. So we can write our Hamiltonian in this sort of general form as the ij inverse u sub l, p sub I, j, plus u sub l. And just as another note, remember that we're only ever dealing with conservative systems here, so systems which conserve energy. Okay, and final note is that we are, of course, using the summation convention, where if you see a repeated index in a product, that means that that index is summed over in that product. Okay? So, this funny Gij inverse thing, we found that we can find it from a set of Cartesian coordinates. So if I have some set of Cartesian coordinates, coordinates xi, then I can find Gij inverse q sub l equal to the sum over k, 1 over mk, where m is the mass of this kth degree of freedom, right? Because remember, we have to have one coordinate for each degree of freedom. So this is just the mass corresponding to that degree of freedom. And then we get dqi, dxk, dqj, dxk. And we also found that this guy, which we can find from the chain rule, is going to transform G inverse. It's going to go to some G inverse prime, which should be equal to, if I'm not mistaken, dqi dq prime. Wait, sorry, I'm messing things up here. Apologize for this. Have to remember all of my indices correctly. So this should be dqi, dq prime l, dqj, dq prime. Okay, I believe that's the correct indices. I mean, we can get it just by using the chain rule in this first expression, right? dqi dxk is equal to dq prime, I guess I'll call it L, dxk dqi q prime L. Okay. So now from this, we can get our equations of motion, our Hamiltonian equations of motion, which are qi dot, so the time variation of our coordinates is given by the derivative with respect to the conjugate momenta, and the time variation of the momenta is minus dh dui. So these are Hamilton's equations of motion that we will be using quite frequently. Okay, so now one thing that I want to note, just, well, there's a couple things that I want to sort of get out of the way, is that a lot of times when we are doing these coordinate changes, we want to find the most convenient coordinates that we can possibly work in. So oftentimes it involves like translations, so just shifts side to side, up and down, back and forth, all that, or rotations. And the nice thing about this is that as long as we're just doing translations in particular, the form of Gij will never change. We will never change Gij inverse. And that's pretty simple to see because G is just given in terms of derivatives, and G's transformation rules are also just given in terms of derivatives. In particular, right, if I have, I don't know, something like this, where Qi is equal to Qi prime is equal to Qi plus, I don't know, some constant shift a sub I, then obviously this derivative is just going to be 1 because this constant's going to drop out. So that one's easy to see. So I'll just write that really quick. So G inverse Ij is not affected by translations. So that's pretty nice, and as we'll see with the first example, this is actually, I mean, it's super useful because it allows us to sort of play it fast and loose with where we're defining our origin in particular. We can always move around our origin and kind of say we don't really care where it is. It's mostly because this guy will never be affected by just constant shifts in origin. The other thing I want to note about this matrix is that if we start with Cartesian coordinates, then our kinetic energy term, which I'll just write T, and I'll just restrict to a single particle in any number of dimensions. So in that case, we just have this. So this is our kinetic energy. So if you notice, this here, this is the magnitude of the momentum vector. And in particular, one thing we know about a magnitude is it's just a fixed thing, right? It's just a number. The magnitude is a number. It doesn't have any direction. It doesn't have any preference like that. So in particular, if we're starting in some Cartesian basis like this, and we rotate, this kinetic energy is never going to change. It can't, because it's the magnitude of the momentum vector. And so if we start in a Cartesian basis, then rotations also will not affect G inverse Ij, right? Because the form of this kinetic energy term will never change, and so, of course, if the kinetic energy is not changing, then G inverse isn't changing. Another way of seeing it is just seeing that Gij is going to be proportional to the Kronecker delta. And if I have rotations, so something like this, delta JL R LK, this is again just equal to Kronecker delta. That is, I don't necessarily expect that to be obvious, but if you write down a rotation matrix and do this all out, you should find that this is correct. Okay. And of course, you can find the rotation matrix by just looking at these derivative terms. Okay, so with that out of the way, let's look at an example. So I don't want to start with gravity because gravity is kind of complicated, and we haven't done much with this Hamiltonian formalism yet, so I want to start it off a little bit simpler, a little bit more straightforward, but hopefully still interesting. Interesting to the point that you'll see that the system is at least it would be decently difficult to look at in the Newtonian formalism. So in particular, what I want to look at is a system where I have a frictionless slope, and I'm going to put two masses on this frictionless slope. So we'll say this is m1, and this is m2, m2, and they're connected by a spring. Okay? So already we see this, this is going to have to take some thinking to set up in Newtonian mechanics. It's a fairly complicated system because, we have force due to gravity. Well, I'll just say we have an acceleration due to gravity g, and this slope is at some angle theta. And so this might take some work to draw all our free body diagrams and write down the sum of our forces, yada, yada, yada. But with this Hamiltonian setup, we can just pick a set of coordinates, just start with some set of coordinates, which we think might be convenient. In particular, we'll call these coordinates Q1 and Q2. And the easiest thing to think of is just their positions on the slope, right? I mean, we could think of starting from some two-dimensional Cartesian basis, rotating, translating, and all that, but we already know that rotations and translations, if we start in a Cartesian basis, aren't going to affect anything. It's also nice because since the masses are restricted to a slope, this is a one-dimensional problem. So, I mean, just counting degrees of freedom, this should be all we need. Since we have two masses in one dimension, so we need two degrees of freedom. Sorry, I did get a bit sloppy. There's a question about how pi can be the magnitude of the momentum if it has the units of momentum squared. Yeah, I got a little sloppy. This isn't the magnitude, this is the magnitude squared of the momentum. So really, the magnitude is the square root of this. But still, the magnitude squared is still just a number. Yes, Narf, we of course always want to pick the coordinates which allow us to be the laziest as possible. But as we'll see, this is actually not the set of coordinates which allows us to be the laziest as possible. But I'll save that for later. So as I said, I mean, these coordinates, they're going to have their origins shifted from each other, but at least in the case of the kinetic energy, we don't care. It's not going to affect anything. So in this case, we can just write down our Hamiltonian, which I'll write Q sub L, P sub L is equal to, well, 1 over 2 m1, P1 squared, where P1 is the conjugate momentum to Q1, plus 1 over 2 m2, E2 squared, or of course E2 is the conjugate momentum to Q2, plus our potential energy, which is going to be a function of Q1 and Q2. Okay, so now we want to focus on what this potential energy is. Well, in this case, we have two sources of potential energy. In particular, we have one, which is the potential energy coming from the spring, and then another one, which is coming from just gravity pulling down on both of these things. The spring potential energy we know. This is just 1/2 kd squared, where d is the distance that this spring is stretched from equilibrium. So I'll write this as d minus L naught. L naught is this equilibrium distance, where this essentially the distance that the spring wants to be at. It wants to sit at some length L naught. Yeah. So I know that this distance is going to be at least related to Q1 and Q2, the difference between Q1 and Q2, right? Because if I fix Q1 and I pull Q2, d gets larger. If I do a similar thing with Q1, d might get smaller, so on and so forth. So I can say that d is equal to Q2 minus Q1, and then minus L0. Okay, the minus L0 is just there to say that, okay, hey, when these guys are when their difference, 2 equals L0, and actually I think this is, I don't think this is quite correct here in my notation, but so I'll just erase that. But so anyway, what this is saying is that when Q2 and Q1 are separated by an amount L0, then the potential energy of this spring is just 0, right? It's sitting at its equilibrium. It doesn't want to stretch. It doesn't want to compress. It's happy where it is. Okay? So that's what this added L naught is for. But it's completely unnecessary, right? Because we know that we can just shift either Q1 or Q2 by an amount L naught minus L naught. We could shift both Q1 and Q2, whatever. It's just a constant shift. So it's not going to have any effect on our kinetic term, namely these guys. So we're completely free to define Q1 and Q2 so that d is just Q2 minus Q1. We have that freedom completely. Okay? So our spring potential, in terms of Q1 and Q2, we can just write as 1/2 k, which is just the spring constant of our spring, Q1 or Q2 minus Q1 squared. Okay, so now the gravitational potential energy, well, we know what the gravitational potential energy of something is. It's just mgh. The mass of the object times the gravitational acceleration times the height. And in particular, since we have two things, we have to add both of the contributions. So this is going to be m1g h1 plus m2g h2. So now we just have to figure out what h is. And here's where sort of the trickiness of this is. Notice how I defined Q1 and Q2 to be pointed down the slope, right? This is, of course, completely arbitrary. I could define Q1 and Q2 to be pointing up the slope, But I just did this because, you know, we have some sort of physical intuition and we expect these things to evolve down the slope. They want to go down the slope. So I just defined Q1 and Q2 so that their evolution would be positive. And the reason being is that we'll hopefully avoid a bunch of dropped negative signs here and there. Like I said, it's completely arbitrary. But so now we do have to be careful because we might want to say that, for example, H1 is M1 G Q1 sine theta, right? Sine theta just coming from this right triangle here. But there's sort of a few ways to think of this. The simplest one, in my opinion, is that we want potential energy to decrease when the system evolves in the favorable direction. So we know in this case that the favorable direction is going to be down the slope, which means that Q1 and Q2 both get more and more positive, which means that the potential energy must get more and more negative. And so, you see, we have to have some minus signs here. And similar for H2. Sorry, these aren't H2. H2 is just this. And H2 is minus Q2 sine theta. And of course, there's some constants as well in these, but we don't care about those because that's just going to add a constant to our potential energy, and when we take derivatives of the Hamiltonian, those just drop out. But so hopefully this minus sign makes sense. Another way to sort of see it is that when I take the sign of this, I'm really, right, this is the sign of a vector, and so this vector can be made up of something which looks like this, where the y component is pointing in the downward direction. Whereas when I'm looking at a height, I want to be measuring it from the ground upwards. So that's how you can sort of see another origin of the minus sign. I personally prefer to think of, okay, how will the system evolve so that the potential energy will get smaller? But anyway, so we know that the gravitational potential energy in terms of Q1 and Q2 should be minus what's the simplest way to write this? M1 Q1 plus M2 Q2 sine G sine theta. So when all is said and done, we can write down our Hamiltonian. U sub L, P sub L, 1 over 2 M1, P1 squared, plus 1 over 2 M2, P2 squared, plus 1/2 A2 minus Q1 squared minus M1 Q1 plus M2 Q2 G sine theta. Hopefully that's not going off the screen. Just barely on. Perfect. Okay, so now's where everything is completely mechanical, right? We just plug this into Hamilton's equations of motion. We get Q1 dot, Q1 dot is dH dP1, which is, of course, just P1 over M1. Q2 dot is P2 over M2. And then P1 dot is equal to M1 Q1 double dot, just solving this first equation here. And when we take derivatives and everything, minus K Q1 minus Q2 plus m1 g sine theta. And then p2 dot is 2q2 double dot minus k q2 minus q1 plus m2 g sine theta. And there are our equations of motion. And, you know, this is all well and good. Awesome, we have equations of motion, blah, blah, blah. But you can kind of see this isn't really the easiest thing to look at, right? These are two coupled second-order differential equations, which, you know, yeah, you can solve this, but it's not the easiest thing to do. But yeah, so we'd love an easier way of doing things, right? So how can we do that? Well, the best way to do it is to simply just change our coordinates that we're looking at. So how do we choose these coordinates? How might we get this divine inspiration to figure out what the best set of coordinates are? Well, as Narf suggested, let's try to make things as simple as possible for ourselves. Do things the easiest way as we can, right? So, in particular, we'll look at this term here, and we'll look at this term here. And we see that, you know, this will simplify pretty greatly if I define two new coordinates. One I'll call delta, reminiscent of what we did when we were talking about harmonic oscillators. And then another one I'll call capital Q. I'm going to define capital Q in a little bit of a weird way. And I'm just going to do it so that it still has the same units as the little q's. So we want the m1q1 plus m2q2. But, you know, this has some units of mass times distance, so we should divide by some mass. And just to keep things completely agnostic towards mass 1 and mass 2, we'll divide by m1 plus m2. Yes, exactly. So I already see in the chat people suggesting use the coordinates of the center of mass. That's exactly what this guy is. And we'll sort of see how this becomes the center of mass. Well, I mean, right now. So now when we plug these guys in, we can see that our new potential energy is given as 1/2 k delta squared, and then minus m g q sine theta, where m I've defined as just the total mass of the system. Okay, excellent. So now this looks far simpler, right? I mean, it really just looks like two completely separate systems. It looks like what we would expect from a harmonic oscillator, just some 1/2 kx squared. And then something falling in a gravitational field, where it's acting on some degree of freedom q, which, as Hans mentioned, is the center of mass, right? So, well, let's crank through everything and get our equations of motion using this. Well, to do that, we have to figure out what our new kinetic energy is. And to do that, we have to know a few derivatives, q1. And, you know, I'm going to go pretty quick through this part because, you know, like I said, it's pretty mechanical. You turn the crank, you take the derivatives, and you go on your way. m1 over big M. But if anyone wants me to sort of stop and explain a step in a bit more detail, feel free to let me know in the chat. And so then in this case, we can use our transformation rules to find our components of G, and we get something like d delta 1 squared plus 1 over m2, d delta dq2 squared 1 over m1 plus 1 over m2, which I'll define as 1 over mu. I'll explain what mu is in a second, or give a name to mu in a second, more than anything. G delta q. Again, just sort of plugging in derivatives into our transformation rule, we get something like 1 over big M. This, so our off-diagonal elements are 0, which is always nice. And G inverse QQ is just M1 plus M2 over big M squared, which is just 1 over big M. So I've introduced this guy here, so I should probably define it a bit more. 2 over M1 plus M2. This is known as the reduced mass. Reduced mass of the system. And the reason why it's called the reduced mass is because, so if I say let M2 get very, very large, you see in the denominator, M2 dominates over M1, and so the M2s will pretty much completely cancel out, and mu will end up being equal to M1, which is the smaller of the two masses. So mu is known as the reduced mass. I'll refer to it as such from here on out. So writing our Hamiltonian in this form, in terms of delta q e sub delta e sub q, we get something like 1 over 2 mu e delta squared plus 1 over 2 m e sub q squared plus our potential energy minus m g u sine theta. Now we just plug this into our equations of motion, of course, as always, as we always do. And again, without going through the steps super explicitly, we get, well, what we might exactly expect. We get two equations like this, where, of course, this just looks like the harmonic oscillator. And this is just a free-falling body. So here's the sort of punchline of all of this. If we were to do things in the Newtonian formalism, right, for the most part, what we would do is probably write down something like this, and after some sort of thinking, we might be able to, sort of logic and reason our way to these. Sure, we might be able to get them, but more or less what we'd end up with is this coupled set of differential equations, and then we'd try to brute force solve this. Whereas here in the Hamiltonian formalism, all we really had to do is say, okay, well, what coordinates make things easy? And then we use those coordinates, which make life easy, and we get a nice decoupled set of differential equations. And so if anyone is interested, this is what the solutions do. So here's some 3 different cases where the masses of the two blocks have different ratios. So, Of course, as we might expect, it just looks like 2 blocks on a spring going down the slope. Okay, so yeah, and so this is cool. And of course, we can solve these equations. We can plug back in Q1 and Q2 in terms of these deltas and big Qs, all that stuff. And what we'll of course find is that those Q1s and Q2s satisfy these more complicated couple differential equations. Okay? So I'm going to take a quick pause here. I think that the rest of the stream I want to entirely devote to gravity. So if anyone has any questions before we get going on that, please do let me know. Yeah, I'd be happy to answer any questions people may have. Yeah, so hopefully at the end of the day, this is, we get some sort of appreciation for the fact that this is all mechanical, far less thinking than Newtonian mechanics. Yeah, so I'll get to both of these questions in chat. So Narf says, I don't see why it's so much harder to do in the Newtonian formalism. Can't you do the same coordinate transformations? Yeah, and actually this is a fairly straightforward one to do in the Newtonian system. Just by thinking about, well, what's acting on what? Well, we know gravity is acting on the system as a whole, right? Gravity is an external force, so it's never going to change the internal dynamics. So it, of course, has to only ever act on the center of mass. Whereas the spring has to conserve the total momentum because it's an entirely internal force. And so, yeah, like I said, we could, of course, intuit our way to these, make these coordinate transformations, blah, blah, blah. In the standard Newtonian formalism as well. Yeah, I don't disagree with that at all. It's just what I'm trying to get across is that we didn't really need to think, right? We just looked at the form of the Hamiltonian, asked what is the simplest thing that we can do, and we got the decoupled equations. And also got some insight, right? We got this insight that gravity is only acting on the center of mass, and then the spring force is only acting internally, and so it's almost backwards, right? In the Hamiltonian formalism, we go in with knowing a lot less information, and then we get that information out. Whereas in Newtonian mechanics, we sort of have to have a lot more intuition beforehand to simplify the problems. Hopefully that makes sense. So the inverse G matrix. Yeah, so the inverse G matrix. Yeah, just question to clarify this inverse G matrix. I'm not sure exactly where the confusion was, but a lot of this was explained in the last stream. But essentially, this inverse G matrix that we introduced in the form of the Hamiltonian up here, it's essentially just to sort of bookkeep for the fact that when we make these coordinate transformations, it might change our form of the potential energy. Or, sorry, the kinetic energy. Of course, it's going to change the form of the potential energy as well. But so this we found this. It's I don't expect it to be obvious that, oh, of course we need this G inverse. But we found that this was necessary to include in this way. And just that it has these certain properties that allow us to find it and sort of just plug in the elements. Again, without doing as much thinking. right? So sorry if that's not a super satisfactory answer, but I don't think it would be the best use of time here to rederive all of that stuff. But yeah, I mean, I would just say, you know, if it's deriving the elements of this, yeah, I sort of intentionally went through that quickly because it's, you know, taking derivatives, plugging the derivatives in, and getting the answer out. So these steps, I don't necessarily expect to be super obvious if you haven't done them yourself, but you can sort of take my word or don't take my word and do it yourself, and it's a good exercise. Yeah, so yeah, it seems obvious which transformation to do because we got that information from the Hamiltonian. Yes. So in Newtonian formalism, we got some intuition from doing other problems as well, and so we can apply that in the future, but in this case, we don't necessarily need that intuition. We can just sort of look at it more mathematically, which some would argue isn't as much of a benefit as I personally would, because I like just to be able to be, as Narf says, as lazy as possible. Okay, so now I think I want to move on. I think I want to move on to talk about some gravity. And in particular, we'll do gravity. We'll treat gravity sort of as general as we can, while still keeping it simple and in principle solvable. So we'll consider two stars. So we'll make a blue star, and we'll make a red star. And we'll say that these two have different masses. Call this M2, call this M1. But we won't necessarily assume that we're not going to make any assumption like this. We're going to allow these things to evolve just as they would. We're not going to look at any limits or any of that. So that like one of these is fixed and the other is moving. No, none of that. We want to be able to look at this so that both of them evolve, which of course is going to make the problem more complicated, but that's okay. So first thing is we already know that this is all going to be restricted to a plane, right? I mean, we can see it pretty easily that it's going to be restricted to a plane because I can describe it by just two vectors. Call this x1, call this x2. And two vectors, no matter how I orient them, however I twist them around, two vectors are always going to form a plane. So these always have to be in a plane with each other, right? Just guaranteed, because the vectors have to form a plane. I can have two vectors living in 4 dimensions, but really they're always restricted to a plane with respect to each other. Now, if I put in a third planet, I couldn't say that. I of course couldn't say that this isn't in just 2 dimensions, but for right now, we're just concerned with the 2 stars, so we're going to restrict ourselves to 2 dimensions. So we have 2 stars in 2 dimensions, which tells us that we need 4, we have 4 degrees of freedom, and we need 4 coordinates. We'll start with these ones, and we'll just call this x1, x2. These are just our standard Cartesian coordinates. Completely stupid to use for this situation, right? Because it doesn't respect any of the symmetries, it doesn't do any of that, but it's a good starting point for Hamiltonian mechanics. And we know that the potential energy, so x1 L x2l is going to be given as g sub n m1 2 over magnitude x1 minus x2. Right, this is something that we found previously. We derived all of this in a previous sense, where this vector here is, of course, just going to be, well, I think in this case it's x2 minus x1, but minus x1. So it just is given by the distance vector between the two, or the length of the distance vector between the two stars. I'm going to rewrite this in our index notation just to, well, sort of unfairly emphasize how messy this is. And this is going to be something like x1 sub I minus x2 sub I, x1 sub I minus x sub I. Okay, and this is, of course, all in Cartesian coordinates, so we know the form of the kinetic term. And so we can write our Hamiltonian immediately. Do m1, p1 sub I, p1 sub I, plus 1 over 2 m2, p2 sub I, p2 sub I, minus this awful monstrosity. Yeah, x1 minus x2, x1 minus x2. Okay, this looks horrible. This looks absolutely awful. I'm not even going to bother dealing with the equations of motion in this form because they're just going to look completely ridiculous. So the very first thing we're going to do is find some new set of coordinates. And immediately we see, hey, this looks familiar. This is just a distance, right? Which we saw in the last one. If we use something like delta I equals x1 minus x sub I2, this should simplify. And automatically you see that it does. It immediately simplifies what's in this square root. As for the other coordinate, yeah, I mean, we could go through things and try it out, right? Because this only gives us 2 degrees of freedom, only gives us 2 coordinates. And so just sort of by analogy to the last one, we might expect, hey, this might be a useful coordinate again. Our center of mass coordinate might be useful again. Now, we don't have any indication of that from the form of the Hamiltonian, right? Because this guy here is it's not simplified by this, but actually we kind of do, because of the fact that if you work out all of these components of the inverse of G, you'll find that specifically this guy, the derivatives interact, or the derivatives of delta and capital Q interact in a way that if you choose something else, this will not be 0. So in fact, by choosing this Q sub I, we are really still trying to make the form of the Hamiltonian as simple as we possibly can. It's just in a little bit more obscure way. And this, of course, is something that I really encourage you to try out for yourself, but I feel like I think I've done enough taking derivatives in front of you guys to justify going through that super slowly. Unless people want me to, of course. So again, sort of by analogy of what we just saw, you can do this yourself if you're really inclined. But what we find is some that are Hamiltonian. I'm actually gonna write this way just to sort of try as hard as I can not to confuse conjugate indices, or the indices which pair the momenta to the variables with the vector indices. And then this just becomes Gn m1 m2 over the square root of delta I. Okay, so and of course I've kept the same reduced masses, so this is m1, m2 for big M, and big M is the total mass again. And again, I'll just reiterate, I don't expect this to necessarily be obvious that the Hamiltonian takes this form. It's just, I know sort of last time people were getting a little bit tired of watching me take derivatives in front of you, so I wanted to go through this a bit quicker. Okay, so we can already see something very cool happening. And we see that H, our Hamiltonian, does not explicitly depend on any of the center of mass coordinates, which in particular tells us that, write this, keep my notation consistent, this d u sub I, this is 0. In other words, the momentum conjugate to q sub I is conserved. Always, period, end of story. Done. And in fact, we can see that this is completely generalizable. Ignoring gravity, ignoring any particular system, if we have a Hamiltonian, such that it doesn't depend on one of our coordinates, just call it Q, then that means that P conjugate to Q is necessarily conserved. Oh, geez, I had to have spelled that wrong. This is very cool. This is sort of a big deal, because now we can just immediately look at our Hamiltonian and know if we have conservation rules. And of course, we can rephrase this in terms of symmetry, where we can say instead, alternatively, if H has a symmetry under Q going to Q plus A, where this is a constant. So again, just a constant shift. We know this constant shift is never going to affect the kinetic term, so all the other dependencies are going to show up in the potential energy. So if this shift doesn't actually affect H, then it's the same thing as saying this, that H doesn't depend on Q. So if our Hamiltonian has this symmetry, this necessarily means that, again, EQ is conserved. Yeah, conserved. So again, we're seeing more and more, and in this case, it's completely general, right? In the Newtonian case, we saw it explicitly for linear momentum. We saw it for angular momentum, but in this case, we see it's completely general. If we can choose any set of coordinates where the Hamiltonian is independent of one of the coordinates, we are guaranteed to have a conserved quantity. So again, we're seeing some connection between symmetries and conservation laws. And yes, as Annabelle has said in the chat, this is much deeper. Unfortunately, we're not going to see the super deep theorem right now, but this is actually true in general. If we have any symmetry, there is going to be a corresponding conservation law. Well, any continuous symmetry, I should say. But okay, so this is exciting. And in particular, we can see by the form of this Hamiltonian that the terms involving anything to do with Q, so in this case, our PQs, our conjugate momenta to Q, they never talk to any terms having to do with delta, right? So we don't have any deltas in this term, there's no Qs in this term, so on and so forth. This means that these degrees of freedom, as we say, these degrees of freedom are not coupled. And that just means that when we find our equations of motion, right? So when we find our equations of motion by taking derivatives of the Hamiltonian, nothing having to do with Q will ever show up in an equation having to do with delta. Which means that we can actually just completely ignore the fact that Q exists. We can just completely ignore it, pretend that it doesn't exist. And that, of course, just corresponds to fixing a reference frame. Right, we're choosing where to put the center of mass of our system, and that just is, or I suppose, what momentum to give the center of mass of our system. And that's equivalent to choosing a reference frame. So we will, of course, choose the reference frame which is the simplest to deal with, namely the one where we're going to choose PQI equal to 0. We're just going to say this center of mass is stationary. But, of course, we can get to a more general reference frame by just shifting the momentum of the center of mass, which we can freely do whenever we want because we know that it won't affect anything having to do with delta. Hopefully that all makes sense. So I'll rewrite this just in this reference frame, and in particular just in terms of these two things. And I get 1 over 2 mu e delta I minus g n 1 m2 over square root of delta I. So we see that this still isn't as simple as we possibly can get, but it's getting there. It's getting close. And in particular, we see that this is a Hamiltonian for a Cartesian set of coordinates, right? Where our delta I are behaving as Cartesian. But we know that something like this, so delta 1 squared plus delta 2 squared, is going to simplify greatly if I go to polar coordinates, right? Where this is just going to be r squared. So if I define delta 1 equals r cosine phi, delta 2 equals r sine phi, then our Hamiltonian simplifies even more. Well, specifically, our potential energy simplifies even more. And again, this is something that we dealt with last time, going from a Cartesian set of coordinates to a polar set of coordinates, so I'm not going to rederive anything. But what happened to the momenta, just to sort of remind you, is we got a radial kinetic energy term. We also got an angular kinetic energy term. So in particular, I'll write this as HR P sub r, P sub phi, 1 over 2 mu P sub r squared plus 1 over 2 mu r squared P sub phi squared P m1 m2 over r. But what do we notice? We can notice that, again, h doesn't depend on phi. And so we automatically know that p phi, which I'm just going to call L, is conserved. And in particular, if I write down the equation of motion for phi, which is going to be dh dp phi, this is going to be p phi over mu r squared, which I'll write as L over mu r squared. Okay. Now, unfortunately, in this case, we can't just willy-nilly set L to be whatever we want. In particular, you see that this factor of r is showing up in the kinetic energy term, which means that our r coordinate actually does couple to the phi coordinates, or the conjugate momenta to phi in particular. So we can't just set it to be whatever we want, but we can, we know that it's always going to be conserved. We know that L is a constant, and we can include this in our Hamiltonian to mu p sub r squared plus L squared over 2 mu r squared minus gn 1 m2 over r. And now, I hope we can appreciate something. I just want to take a second to appreciate something that's actually quite incredible. It's the fact that we've taken something which was originally a 4-dimensional problem. Right? We had 4 different degrees of freedom in our system. It was a 4-dimensional problem. We would have ended up with a 4-dimensional set of differential equations that we would need to solve, or 4-dimensional set of second-order differential equations that we would need to solve, which would be an absolute nightmare. And just by redefining coordinates, that's all we did. We've completely reduced that to a 1-dimensional problem. Right? This is a 1-dimensional problem in terms of r. So this is sort of one of these beautiful things that happens in Hamiltonian mechanics. You get this massive simplification just by choosing convenient coordinates. And we can actually get a ton of insight just from this, especially if we write this as a Cartesian Hamiltonian, right? So this is a 1-dimensional Cartesian kinetic term where the mass is the reduced mass, plus what I'll call U effective, of R. It's not our original potential energy, but it's a what I'll call a one-dimensional effective potential energy. Just meaning that it only depends on R, this term, and this term only depend on R. So when I combine them, it still looks, in this one-dimensional sense, like a potential energy term. That's all I mean by U effective. And just to define it, 1m2 over R. Okay. And so we can notice that this is just our usual gravitational potential energy plus our centrifugal force term, or I guess we could call it a centrifugal potential energy term. And actually, you can see that nothing about this was really special to gravity. The only thing special about this was that our potential energy to start with only had to do with the distance between two objects. And so, in particular, this is true. I can do all of this in any case where I have a potential energy which is only a function of that distance between two objects. This is completely generalizable to any, as we might call it, a central force problem. I can always do this. I can always immediately write down my Hamiltonian in this way, which is pretty cool. Again, this is pretty powerful stuff that we're able to reduce something like this to a one-dimensional problem. So I think now might be a good time to take a quick break, see if anyone has questions, sort of try to let people absorb all of this stuff. And then we'll look at this effective potential a little more to try to get a little more insight into what's going on, and then we'll actually solve this and have, find our solution for Newtonian gravity for two bodies. So hopefully in this case, you scroll up to the Hamiltonian with the 4 degrees of freedom to compare. Yes, so I'll circle things to make it even better. So this is our one-dimensional effective Hamiltonian. Or not effective, this is our actual Hamiltonian with 1 active degree of freedom, we might say. And our original Hamiltonian was this guy here. This was our, actually, that's not even our original Hamiltonian. This was our original Hamiltonian. It's quite disgusting, and even simplified is still not particularly pretty to deal with. And if I were to write down the equations of motion, you would see how massively simplified this is. I mean, especially for this first set, the equations of motion are going to be completely awful. Yeah, I agree with you. Annabelle said it's definitely more rigorous than Newtonian mechanics, but in some way more beautiful. I think those things might go hand in hand. Not that Newtonian mechanics isn't rigorous. I do think Newtonian mechanics is quite rigorous, but I think a lot of the time when you have something which is very mathematically solid, there's a lot of beauty to it. in that it's often very powerful when you have a very robust mathematical background to it. So, yeah, I think I agree with you. This is very, very nice. Okay, so hopefully people are fairly good, fairly okay moving on. So the first thing I'll do, I'll just go ahead and write down our equations of motion. I mean, it's pretty simple to do. We just do our standard one-dimensional, take some derivatives, blah, blah, blah. And what we find is something like this: L squared over mu r cubed minus gn m1 m2 over r squared. This is our one-dimensional equation of motion, and I should give it a friend, that being really the other active equation of motion, which is just our conservation of angular momentum equation. But you see, again, I can solve these entirely independently of each other. I can solve the R equation first, and then phi equation. That's not actually what we'll end up doing, but in principle, I could. I mean, this is a pretty horrible differential equation to solve still, but I plug something like this into a computer, and it'll solve this a heck of a lot faster than it would that original set of differential equations. But so before I get too deep into actually solving this and everything, I want to take a bit of a closer look at this effective potential energy. I'll just rewrite it down here for us. This is L squared 2 mu r squared gn m1 m2 over r. So this is our effective potential energy. So I'm looking at both of these, right? I can look at both of these, compare them, and what I can see is that, so the centrifugal force, the potential that I get from the centrifugal force, it's positive, so it has a positive sign, and it dominates at short distances. Dominates at short distances. Right, because when I get very, very close to 0, say, when I get close to r equals 0, r squared is going to blow up much faster than 1 over r. However, this guy here, obviously, overall, it comes with a negative term, or negative sign. And this is going to dominate at long distances. And the reason being is that as r gets very, very large, 1 over r squared is going to drop off much faster than 1 over r. So in particular, I might expect a plot of each of these. So if I look at, say, the centrifugal force and the gravitational force, this might look something like this. It's very large near x or r equals 0, but then let's see if I can draw this even more exaggerated. And then it's going to fall off quite quickly for large r. It's going to asymptote to r equals 0. Whereas this guy, it's not going to be as large, but it will. This won't be perfect how I'm drawing it, it will stay larger for longer. This isn't a perfect drawing, but it's sort of exaggerated, right? So I can think of this as being 1 over r squared, and this is minus 1 over r. Do that in blue. Again, this isn't perfect, but it's sort of to exaggerate the features. In particular, these two things are competing. They're competing against each other. And when we look at a plot, which let me pull that up real fast. That should be here. So here's a plot of this effective potential energy term. And so you can see that at short distances, so when r gets closer and closer to 0, the positive part, which is the 1 over r squared piece, the centrifugal part, that's going to dominate. That's going to take over and drive this effective potential energy up. However, at long distances, the gravitational potential energy sort of takes over. And so you see that they're competing, but in these different limits, they sort of dominate in differently. However, in between, their competition becomes sort of equalized. And we get these places where the effective potential energy flattens out. It goes to 0, or the slope goes to 0. And that seems like sort of a special point, and because that's sort of the point where this competition sort of cancels out. That no one is winning over the other. So let's look at that point in particular. And I mean, we know that if the slope is flat, that's equivalent to the derivative vanishing, correct? So we'll just take a derivative of this effective potential with respect to r, which I'll just designate by a prime. And this is, not L cubed, sorry, over mu r cubed minus plus gn m1 m2 over r squared. Want that equal to 0. And of course I can solve this however I want. I'll just move one term over to the other side. Squared over mu r cubed. But here's the thing. This is exactly, if I plug stuff in, if I plug in L and all this stuff, I find that this is mv squared, that's mu v squared over r. So this requirement becomes the same as the requirement for circular orbits. Right, because this is the centripetal force acting on an object traveling in a circle, where v is the tangential velocity. And this is, of course, just the gravitational force, the magnitude of the gravitational force. And when the magnitude of the gravitational force and the centripetal force are equal, it's traveling in a circle. So this minimum point of our effective potential energy is actually telling us what radius we have to be sitting at for a given choice of L that will have a circular orbit. And in particular, we can actually solve for this radius, which I'll call RC, in terms of all of our other junk. Vn mu m1 m2. Pretty cool stuff. But this isn't really the end of the story. This isn't the end of the neat stuff we can do. In particular, we know that we can sort of, well, we know that potential energies are going to always want to decrease, correct? So if I draw this effective potential, I know that it looks something like this. Put an arrow to hide my mistakes. So this is U effective, and this is R. The potential energy always wants to decrease, and this is no different here. I'm just treating it as a one-dimensional problem, and the one-dimensional potential energy, which is U effective, is always going to want to decrease. Which means that I can sort of almost think of this plot as a hill. And I can place a ball on this hill, and how the ball would roll up and down the hill is just how the system evolves in this potential energy. So in particular, you see that if I drop a ball, I'll make the ball a different color. If I just drop a ball at the minimum point here, which of course this is R sub c, it's never going to move. It's happy sitting at the bottom of the hill, and it's never going to move. And so that tells us that R will never change, but that's just saying the same thing as that the stars will be in a circular orbit. However, if I were to drop a ball, say, up here, you see that this ball will roll down, make it to some other point that's the same height as its original height, and then it'll roll back down and up here, and then it'll just oscillate between those two. This is an orbit. This is a stable orbit where I have some let's call it R0, R1, and I have some close point and some far point, and the stars are just gonna orbit each other between these two distances, and they're always gonna stay orbiting each other. But we can see that's not always gonna be the case. In particular, we know that as R goes to infinity, the effective potential goes to 0. And this is never going to cross back, so this red plot will never cross back over the 0 axis. So I'm not going to end up with anything like this or anything wild like that. So you see that if I started a ball, say, up here, it's going to roll down and roll up, and it's going to have enough energy to keep rolling and rolling and rolling and rolling and rolling all the way out to R equals infinity. So this is an unstable, what we would call an unstable orbit, right? The stars come together, they come really close together, and then they fly apart, and then they never see each other again. And you see there's some sort of magic number here, magic value of the initial effective energy, potential energy, where it just makes it to infinity, right? When U effective is 0, it's going to just barely make it to infinity. So there's going to be some minimum radius, which I'll call R min, such that when we put the system there with a given angular momentum, that is the minimum value, that's the minimum distance they can be together to where they'll actually be in a stable orbit. Well, in that case, if you put it there, it will be unstable. But as long as I have the, I'll write this, it'll make it more clear. So if R is always greater than R min, I will always have a stable orbit. But if r is less than or equal to r min ever, and this is ever, if it ever evolves to where r is less than or equal to r min, this will be an unstable orbit. And the stars will fly apart to infinity. So let's solve for what this r min is. It's easy enough to do. It's just the requirement that u effective at r min is equal to 0 for the case where r min is not infinity. And that just gives us an equation to solve. Mu r min squared Gn m1 m2 over r min, which of course we solve for r min to find L squared over 2 Gn mu m1 m2, which we can notice is our circular orbit radius. It's just half of the circular orbit radius. So if our stars ever get closer than half their circular orbit radius, then they'll fly apart and never see each other again. Okay? So the last thing I want to do is actually solve this stuff. So, okay. Feel free to type up questions in chat and everything. I'm going to take a pause. I want to sort of debrief what we just did, sort of reiterate on some ideas, some key ideas. So we have a few key ideas here. And the biggest one is that we have gotten a ton of information without ever actually solving the problem. We just got this U effective. We found the condition for stable orbits, we found the condition for unstable orbits, and we found the condition for circular orbits, which is actually huge. I mean, that's a ton of information. We don't have the exact evolution of the system, but it's still a lot of information packed into never actually solving the dynamics. So I see a question from Narf. How do things ever collide? Well, I mean, in particular, if L squared is 0, then you can see they can, yeah, sure, they can collide. It's okay. If things are point particles, they will never collide if they have a non-zero angular momentum. If they're point particles, and that seems to be what you're saying. Yeah, the size of the objects, if the objects are, large enough, then they'll collide that way. Or if they have no angular momentum. You can see that if L squared is 0, then our effective potential energy just looks like this, and things will come down, down, and just keep evolving all the way down to 0 radius. But obviously, when things get close to colliding, there's a whole bunch of extra messed up stuff that happens. You have tidal forces, you have all that stuff. We're assuming that these are all fixed. Actually, we're assuming that these are point objects, point particles, and not extended objects that have a bunch of extra complicated dynamics. But yes, you're exactly right. The objects will collide if they have a large enough extended radius. But point particles will never collide if they have a non-zero angular momentum. But they also have no size to them. So that shouldn't be too crazy of a statement to make. Water. Okay, so now just for the fun of it, we have equations of motion. let's see what this system actually is describing. Now, all this stuff may seem, as I called it before, divine inspiration, but keep in mind that this problem had people staring at it for a very long time before it was solved. So the step, specifically this first step, might not seem intuitive at all, and that's okay. Don't get discouraged if it doesn't make sense why we're doing it. At the end of the day, it's a hard differential equation to solve, and this is the method people found that solved it. So it's more of a mathematical trick than anything else. But I mean, perhaps one of the ways that we can see is we want to really abuse the fact that we have a conservation law. And so to do that, we're gonna rewrite all of our time derivatives using the chain rule. D phi dt d phi. Well, we know that this is a constant. And so I'll write this as L over mu r squared d phi. Again, if this isn't obvious, that's fine. I don't expect this to be, oh yeah, of course we rewrite our differential equation in terms of phi. But it works, and that's sort of my hand-wavy justification, is we're just going to abuse the heck out of the fact that we have conservation, or a conserved quantity. Another thing that, again, it's not entirely obvious to do this right away, but you see that we have these annoying factors of r in the denominator. And, these kind of suck to deal with solving differential equations. So we're going to just redefine our variables so that in terms of some y, which is going to be 1 over r. Just invert this. And of course, taking these two steps for granted, as I said, I don't expect these to be entirely obvious as to why we're doing this. But I can rewrite my time derivatives, well, my first time derivative acting on r, in terms of derivatives in terms of phi and y. So I get something like this, 1 over y. Right, this guy here is coming from this 1 over r squared there. And this, of course, I can simplify nicely, minus L over mu y prime of phi, where now prime is a derivative with respect to phi. So now I take a second derivative, so then d2r dt squared. This is just a time derivative of this stuff. And when I do all of this nonsense again, I get something like L squared y squared over mu squared times y double prime of phi. And now you'll see why we're actually doing this, and it's because it makes the differential equation much, much, much simpler. When I write it out in terms of y's and phi's, I get something like this. This is equal to L y cubed over mu minus g n m1 m2 y squared. Now I'm going to just divide everything by this prefactor. And we see, sorry, give me 1 second. I think this should be, I think I dropped a square somewhere, or I added too many squares. Ah, yes, this should be L squared. Sorry. Yeah, so then I divide by that prefactor, and I get something which looks like y double prime of phi is equal to y phi minus, well, gn mu m1 m2 over L squared, which is just y of phi minus 1 over our circular orbit radius. I'm going to rewrite our 1 over our circular orbit radius as yc. Again, just to sort of make life a bit easier. And actually I dropped a minus sign as well. So this should be minus, this should be plus, this should be minus, that should be plus. You see why earlier I didn't want to introduce spurious minus signs when I didn't need to, because I drop them all the time. So this is a simple equation to solve. This is just a harmonic oscillator, which is shifted by some constant amount. And so this is going to have a solution is epsilon, y naught cosine of phi minus delta plus yc, where here y naught is just a constant. Well, y naught and delta are just constants. Y naught is fixed by our initial condition for y, and delta is fixed by our initial condition for phi. But we also know that, you know, our equations of motion aren't going to depend on our specific choice of phi, right? If we, as I said earlier, we know angular momentum is conserved. So we know that p phi is conserved, which means that we have a symmetry under phi going to phi plus, I don't know, a constant. So you see, I can just shift phi to phi plus delta so that this delta term drops out and never actually need to consider it. Because it's just, I mean, this is just rotating our system, and the dynamics isn't going to change when we do that. So, just doing that really quick, y naught cosine phi plus yc. And this leads to r phi equals, and I'm going to shuffle around constants a bit, rc over epsilon cosine cosine of phi plus 1, where epsilon is equal to y0 over yc. So this is our solution in terms of r in terms of phi. Hopefully the steps sort of made sense how we got there. Like I said, this last step is just replacing y equals 1 over r, inverting everything, and then shuffling around constants. So now, we can just go ahead and plug this in to our other differential equation, which is phi dot. And we know this is L squared over mu r squared. And then we can just plug this solution in, and we get L squared over mu rc squared cosine phi plus 1. And here is why I said this is almost solvable. Because now we have essentially a horrible transcendental system of equations that I'm not even going to bother trying to solve, and I'll just say, okay, solve this part numerically. I'm not sure if this actually has an analytical solution or not. This one might. It's a first order differential equation, which sometimes you can get around the transcendental problem, but I'm not completely sure on that. So solve this numerically. But of course, now we have just a single thing to solve numerically. Single first order differential equation to solve numerically rather than 4 second order differential equations to solve numerically. Okay, so now I want to go back to this solution here, our solution for R. And again, I'm gonna jumble things up. I'm gonna rearrange some stuff. And when I do that, I find RC minus epsilon R cosine phi. Right, this is just, I multiply both sides by epsilon cosine phi plus 1, and then subtract the cosine phi term for both sides. Okay, so now the whole reasoning is I want to know what this is. What the heck is this? What's this describing? What do these orbits actually look like? And so now I'm going to shift back to my Cartesian coordinates, which, just to remind you, are cosine phi, and delta 2 is r sine phi. And I plug these in, and I get something like delta 1 squared plus delta 2 squared equals RC minus epsilon delta 1. And now I can square both sides, and I get something, again, just sort of rearranging terms, 1 minus epsilon squared, delta 1 squared, plus 2 RC epsilon, delta 1 plus delta 2 squared equals RC squared. Okay, so now I'm going to look at these two terms. I'm going to complete the square for them. And again, when I do that, I get delta 1 plus RC epsilon, or 1 minus epsilon squared, plus delta 2 squared minus epsilon squared. And this is equal to RC squared over, I believe this is just 1 minus epsilon squared, if I'm not entirely mistaken. Maybe I am. No, this looks good. I buy this. Okay. So now I can just, divide everything by this factor. And what I find is something that has the form delta 1 minus c squared over a squared plus delta 2 squared over b squared is equal to 1, where a squared is equal to rc squared over 1 minus epsilon squared, b squared rc squared over 1 minus epsilon squared. And c is rc epsilon over 1 minus epsilon squared. Okay, so we now can see, well, this is the equation of an ellipse. An ellipse shifted in the delta 1 direction by some amount c. So that's pretty cool. We've now found that, well, at least in terms of the delta coordinates, that our stars are orbiting in ellipses. But this isn't actually the positions of the stars, right? Remember, the deltas describe the distance between the stars. It's the distance vector between the stars. It's not the actual position of the stars. But that's easy enough to find, right? We know that delta I is equal to x1i minus x2i. And we also know x2i is equal to minus m1 over m2 x1 sub I. This comes from ui equals 0. And so just plugging this stuff in, you plug it in and simplify everything out, you find the motion of star 1 is given by, call it c prime, over a prime squared plus x1, 2 squared over b prime squared is equal to 1. Where here, a prime is 1 plus m2 over m1 to the minus 2 a squared, a prime squared. B prime squared is 1 minus, m1 minus 2 b squared, and then c prime squared is 1 plus m2 over m1 minus 2 c squared. And you can, of course, find a similar thing just by using this relation here for the second star. So you see that now we have concrete evidence, concrete proof that the stars are orbiting in ellipses. Which is pretty cool. This is, I mean, that's something that I believe Kepler originally said, that, oh, these things are orbiting in ellipses, and we see that our law of gravitation reproduces that exactly. We didn't necessarily assume that they were orbiting in ellipses to begin with, but we found that by our laws, they have to be. Okay, couple last things. If I have an ellipse, which is centered on the origin, then its foci, in terms of this first equation, in terms of this equation here, so if I pretend C is 0 here, then the foci of the ellipse, foci, I never exactly know how to pronounce that, but they're given by this equation, a squared minus b squared, the semi-major axis and the semi-minor axis, the difference between the two. And in our particular case, this is going to be rc squared, epsilon squared, 1 minus epsilon squared, which is plus or minus rc epsilon over 1 minus epsilon, which is minus plus c. And you can see that this argument holds up because all for the case of the actual positions of the stars, because all of the parameters a, b, and c are just related by a single constant. And so if I plug that constant in, I get the same equation. And so even more, the stars are orbiting in ellipses. Ellipses with a single focus, centered. Well, in this case, we can see that the focus is centered at the origin, but we know that we fixed the origin to be the center of mass, right? We fixed the center of mass to be at 0. So the stars are going to orbit around the center of mass. So again, pretty cool. And again, we didn't have to solve that transcendental equation to get this information. Okay. So now we're going to do one last nifty thing. And that is going to be talking about the eccentricity of this ellipse, of these ellipses that these stars are orbiting around. And if you don't know, the eccentricity, the eccentricity of an ellipse is essentially how far it is from a circle. So, for example, an ellipse which looks kind of like that, this is going to have a relatively low eccentricity versus something which looks more like that. That will have a much higher eccentricity. And this is just a formula, the formula from geometry, given by, again, in terms of the semi-major and semi-minor axes of the ellipse. And plugging in all of our constants and everything, this is just given by epsilon, which, again, makes some sort of sense because we found that this is essentially the ratio of our starting point to where it would be if it were in a circular orbit. So it kind of makes sense that epsilon measures the eccentricity. So we'll notice here that the eccentricity actually has an upper and a lower bound for a squared and b squared being greater than 0. In particular, we don't want the eccentricity to be imaginary, right? So epsilon should be greater than 0, right? We don't want this sum to be negative, otherwise we get an imaginary eccentricity, which doesn't make a whole lot of sense given this interpretation. But we also see that the smallest that this ratio can be is 0. So epsilon can also be less than or equal to 1, as long as a squared or b squared are greater than 0. However, if we allow epsilon to be greater than 1, then that means that one of these two things has to be negative, either b squared or a squared. Right? Because then I'm adding this ratio to 1, and I get something which is greater than 1. But looking back at this equation, what that will do is it'll give me a relative minus sign between the two. And this, with the relative minus sign, is the equation of a hyperbola, which, of course, is not a closed object. This doesn't loop back on itself. So this is, again, going back to this idea that for given parameters, our orbits aren't guaranteed to be stable. And so to see what the sort of bound is, actually, yeah, I'll do that. Yeah, no, because in this case, I said it has to be greater than 0. So as long as these are greater than 0, epsilon can never be 1. But if I allow one of them to be 0 or less than 0, then epsilon can be greater than or equal to 1. So in particular, I'm interested in the minimum case. And that's the case where, of course, epsilon equals 1. So going back to my equation for r phi, in this particular case, I get something like RC over r cosine, whoops, not r cosine, sorry. This is just cosine phi plus 1. But cosine is, again, it's a bounded function. It never gets greater than, so in particular, cosine phi is always going to be between -1 and +1. So the minimum radius, r min, occurs when the denominator is maximized, which is the case where cosine phi equals 1. And so we again find this requirement that the minimum radius where the stars will fly off into unbounded orbits is just the circular orbit radius over 2. So that's pretty cool. We were able, we didn't even have to do this. We didn't have to solve this differential equation in this complicated way to get this information. We just saw it from our effective potential energy. But kind of going back, if we were just to write this down in the Newtonian formalism, this would be this relation would pop up only after we've solved the differential equation, so on and so forth. So that's kind of it. What I'll leave you with is a little animation of these stars for different eccentricities. In this case, the blue star is much more massive than the red star. And you see the different values of epsilon give different orbits, and the cyan dot is the center of mass. So as expected, and this is the numerical solution that I was talking about. So this numerically solving for phi, plugging it into the equation of r, doing all the algebra to get things in terms of the x's, and this is what it spits out, which looks perfectly reasonable and just like what we expect from the math. So, I see Higgsino is here. It's nice to have you here. Great channel. So yeah, that's sort of what I'll wrap up with. You guys are being too kind and so if there's any other questions, I'm more than happy to answer some parting questions. If not, well. Yeah, and I guess let me know if you like this style of animation or what I was doing before. I'm kind of trying to switch up to use more Python since I'm starting to get a little bit of a general disdain for Mathematica. But yeah, the next stream will hopefully have some pretty I think they're pretty cool animations in them. So yeah. How far are we from quantum? Well, if I told you how far we were from quantum, that wouldn't be a surprise now, would it? I mean, it's, yeah, without getting too, I guess there's no reason to really keep things as surprises, but we're getting close. It'll be sort of within the next few streams that we are inspired by Hamiltonian mechanics. Sort of go towards quantum. I'm actually in the process of writing that, the script for that stream. So, I'm getting pretty excited about doing that. But anyway, to have any animations crashing here, like the distances of planets going to zero, and planets. I did not try to get the distances to go to zero, but yeah, we actually had a similar discussion earlier, and the nice thing about these equations is that it's sort of built in that these particles, right? Because all of this is point particles, right? The giving them size is completely artificial. That's just to make it obvious that one has a greater mass than the other. But in principle, these are all point particles, so unless they never have any angular momentum, they won't actually collide. So I never was brave enough to try the case where they didn't have angular momentum, but I'm assuming I would run into some issues there. Yeah, wondering how Lagrangian mechanics fits into this. Yeah, I mean, that's sort of what I've said previously. Is I think this is all a lot better justified than Lagrangian mechanics. So far, it's much more justified than Lagrangian mechanics. We'll see that just Lagrangian mechanics is still very justified, but for a completely different reason. And so I again, without spoiling too much, it will probably be a little bit until we see Lagrangian mechanics show up. But no, don't get me wrong. It's not that I don't like Lagrangian. I'm feeling personally attacked. No, I like Lagrangian mechanics just fine. It's just that, how do I say this? The justification of Lagrangian mechanics, going from a classical approach, is that it gives the right answer. And that I don't like. I don't like writing down a set of equations because it gives the correct answer. I like to have some sort of physical justification for doing that. And I think that, again, starting from classical mechanics, you don't necessarily have that justification in Lagrangian. So that it's not that I don't like it. Lagrangian mechanics is actually far more powerful than Hamiltonian mechanics, in that you get much nicer expressions for these relations of symmetries, and Lagrangian mechanics is typically how you prove this general relation of between symmetries and conserved quantities, which is often cited as the most beautiful relation ever derived in physics. And I don't think I disagree with that, but I do think that it is very unjustified from a classical standpoint. So there's my rant. There's my rant for this stream. But yeah. So I think I might wrap it up there. Sorry, there's one more question. This is probably the last question I'll address, but how did Lagrange come up with it? Was he secretly doing quantum mechanics? So the history behind it is a bit strange. It comes from this brachistochrone problem, which if you don't know what that is, let me sort of switch back. So it's this problem of, okay, so I'm going to start something here, start a ball, mass, whatever it is, and it's going to end here. And it's in a gravitational field, so just mg. What path can I draw so that it takes the least amount of time to get there? It's a pretty tricky problem, right? Because do you draw the path of shortest distance? Do you let it pick up a lot of momentum first by falling in the gravitational field really quickly and then let it travel over? Like, this is a very tricky problem to do, and it was actually unsolved for quite a long time. And so, you know, I don't know the exact history behind it, but I think with Fermat's principle with light, that light doesn't take the path of least distance, but it takes the path of least time. That I think Lagrange and Euler applied to this problem essentially, and there's a whole formalism for doing it. And what they found is that it follows a path known as a brachistochrone. I think that's how it's pronounced, which is, it's somewhere in between these two. It's sort of a generalization of a minimization problem, but it's pretty cool. So never actually secretly did quantum mechanics, and then so the mathematical formalism was invented to solve this problem, and then they basically said, okay, we have the Euler-Lagrange equations, which is, it's the set of differential equations you get out of solving this sort of minimization problem. How can we make it so that those Euler-Lagrange equations reproduce the laws from Newtonian mechanics? And so that's how they found the form of the Lagrangian being T minus V. Basically, when you plug this into the Euler-Lagrange equations, you're guaranteed to get basically Newton's second law. So it's interesting. Well, the history behind it is a bit interesting, because I think that Lagrangian mechanics came before Hamiltonian mechanics, actually, sort of almost surprisingly. Everyone just used Newton's formalism for such a long time. And then I think this came, and then they're like, oh, hey, we can do things in a coordinate free way. But if they were applying Fermat's principle, they were secretly doing quantum mechanics. Yeah, and when you're doing Lagrangian mechanics, you are technically secretly doing quantum mechanics as well. You're just finding the amplitude over a single path instead of all of your paths. Yeah. Anyway, I think I'm going to wrap things up here. I appreciate all the support, all the people who came and watched, all the fun questions and conversations and all that. And of course, as always, if you're watching afterwards, I appreciate the support, and excited to see you guys next time. Bye.